Okay, so how do we actually go about working with these normally distributed variables? Let's say that it's not a standard normal distribution like we looked at in our last video, but it's just a normally distributed video with some other normally distributed variable with some other mean and some other distribution, not 0 and 1. Well, this is a job for our z-score. If we were interested in determining a percentage or a probability, this is what we would do. And this is what we actually did with our M&M's example. We sketched a normal curve associated with the variable. We shaded the interest of region to mark its delimiting x values, and then find the z-score associated with that x value, and then found the probability from our table or Excel using the standard normal distribution command. So let's say that we were interested in determining the percentage of people having IQs between 115 and 140. And this is a normal curve for our IQ curve. It has 100 as the mean and 16 as the standard deviation. So what would be our probability? What we would do is we would find a z-score, right? And the way that we would do it is that we could say, well, first of all, our z-score associated with 115, right? We're saying x is equal to 115 right here. So if x is equal to 115, then what we would do is we would get the z-score associated with that by taking 115 minus 100, dividing it by the standard deviation of 16, and this gives us 0.94 right here, 0.94. We would also get our other probability for that 140, right? We'd say, well, at x equals 140, if we took that z value, we would take 140 minus 100 and divide that by the standard deviation of 16. And again, that gives us a z equal to exactly 2.50. So what we would do is that on our table or in Excel, we could look up those two values and then just use the z-scores to look that up. Now, of course, the other trick is that in Excel, we could actually just look up these numbers directly without even having to go for the z-values, because Excel is very nicely happens to have a command that helps us do that. But what we're looking for is the area in between. And so what we would do is that we would get our standard normal distribution curve, our probability for our larger z value, and we would subtract our probability from our smaller z value, right? And we would get those two to get that area right here. All right, so let's go back to that here in a bit. There's some properties that we could use, though, that are actually really, really helpful. One property that we can apply here is the empirical rule. And you recall we talked about this a little bit in one of our earlier videos, but it goes like this. It says, all right, if you do have a normal distribution curve, a bell-shaped in particular curve with that nice symmetric distribution, what could we say? Well, one property that we can use right away is that 68% of all the possible values of observations will lie within one standard deviation to the right or the left of the mean. 95% of all of the possible observations will lie between two standard deviations to the left and the right of the mean. Right? A third property states that 99.7% of all of these observations would lie between three standard deviations to the left and the right of the mean. That is, almost all of the distributions will lie within three standard deviations to the left and the right of the mean. And as an illustration, you can see what that means. If we had our normal curve, 68% of all of our values fall between the mean minus the standard deviation and the mean plus the standard deviation. If we have 95% of our distribution, it would be between two standard deviations to the left. So that's the mean minus 2 times the standard deviation, and the mean plus 2 times the standard deviation. And the third one states that 99.7 will be the mean minus 3 times the standard deviation, and the mean plus 3 times the standard deviation. Well, we've actually dealt with this before. Let's go back to our M&M's experiment, where we found that we were told that the values of our mean distribution of yellow M&Ms is 14%, and that a standard deviation of 5%, right, of all bags of M&Ms will have that percentage of yellow M&Ms. So let's interpret this 68, 95, 99.7% rule in the context. This is a handout question now. How would we do it? Well, by this rule, approximately 68% would be between 9 and 19%, right? The way we think about that, what we were saying before was that by our rule, if our mean is 14% and we subtract 5%, of course, we get 9%. And if we take 14 and we add 5%, we get 19%. So basically what we're saying is that, well, somewhere between 68% of all of the bags that we ever open will have somewhere between 9% and 19% of yellow M&Ms. So my bag that had 11.5% falls squarely in that group. If we take 2 times the standard deviation, that means that we take 14 minus 2 times the standard deviation, that's 4%. And 14 plus 4% plus 2 times 10, that's 10%. It'll give us 24%. Right? So 95% of all the bags will have somewhere between 4 and 24% yellow M&Ms. And again, if we add 3 times the standard deviation, we would have to take 14 minus 15. Now that would actually be negative 1%, but it would be a very unusual universe in which we definitely had negative 1% of yellow M&Ms. Yellow M&Ms would have to disappear from somewhere else in the universe to happen. So in this case, we would say 0. And 14 plus 15, which is to say 29%. Right, so 99.7% of all bags of yellow milk chocolate M&Ms will have between 0 and 29% yellow M&Ms. As an illustration right here, here it is in the empirical curve, right? We said that, well, okay, yeah, between 9 and 19%. 68% of all the samples that we ever take of yellow M&Ms will be between these values. 95% between 4 and 24%, and 99.7% of all the samples somewhere between 0 and 29% M&Ms. So the idea right here is to determine the observations. If we want to determine our areas, we should sketch the normal curve. We can tell something about the percentages of the values that we're going to get under that curve here. And then we can use that to find our x values and our z-scores right here. Right? So let's run through an example or two. Let's say that we have this one. This is on the handout. It says many airlines have a requirement that members of the cabin crew have a height between 62 inches and 73 inches. That is 5.2 inches, 5 feet 2 inches, and 6 foot 1 inches, right? We want them tall enough to reach the bins, but not so tall that they're going to bump their heads every time they walk back and forth in the cabin. It's just a physical impediment on the way that we get these heights. So the men in the population have a normal height of mean of 69.5% with a standard deviation of 2.4 inches. So in this case, what are we going to do? We want to use Excel to help us find this distribution, right? Find what percentage of men would fall between these two values. So what we're going to do is we're going to use sort of a different command, and we're going to use Excel to help us get this one. We're not going to convert it into a z-value, although we could. What we're going to do is this is going to be much more direct. We're going to use our normal distribution. And in our normal distribution in Excel, this is what we type in, norm.dist, and then we use x, that x value, for either one of the higher or the lower values, the mean, and the standard deviation in 1, right? So in Excel, when you enter in these commands, norm.s, norm.dist, we skip the s this time, and we would put in our height, our x value. We always put in the mean as from our population if we happen to have it, and our standard deviation. And I chose 1. 1 stands for true. Although you could type in true as well into your command in Excel to get this. So this is the way I did it when I entered this in Excel. My higher height, X, was 73 inches. The mean was 69.5, 2.4 inches into 1. That gave me a probability of 0.9276 and a bunch of other digits right here. For our 62-inch height, right, we had a very small probability. But what we wanted to do was that if we wanted to find the probability that we were in between, well, we subtract the higher probability minus the lower probability, and we get our resulting probability of 0.9267. So what we're answering right here is we're answering the question. We're saying, well, approximately 92.67% of the population would meet this restriction, right? Now, if we want to find out what probability what part of the population would not meet this percentage, right? We could take 100% minus 92.67, right? And that would give us something a little bit more like 7.33% who do not. 100 minus 92.67 is equal to that. Does not meet our height requirement. Right? So about 7.33% of the population would not meet that direction. Okay. How about the other way around? What about our observations and the probabilities associated with this? Well, in this case, the Wechsler IQ test, here's another one, gives intelligence scores on a score scale that gives a mean of 100 and a standard deviation of 15%. So let's say that we wanted to find what scores separate the bottom 30% from the bottom 70%. That is, what scores separate those who are in the 30% bottom and the 30% of the top, right? And then we're looking for sort of a middle 40% there, right? 70 minus 30. How do we do it? Well, this is just like what we did before. When we're talking about our z-scores, what we're going to do is that we're going to, this time we're given the percentage, so we use our norm.inv distribution right here. And what we're going to do is we're actually finding the z associated with 0.3, and we're looking for the z associated with 0.70. Right? So if we do that, of course, in our commands in Excel, the way we would do it is we would put in norm.inv, and we put the probability, right? The mean probability goes like this. We put in the probability that we want. That's our alpha number right here. So z alpha 0.3, right? Alpha is 0.3 right here. And in this case, alpha for the 0.70, right? Alpha is 0.7. So we put in our alpha score right here. We put in our mean and our standard deviation from our population, and we put those in here, right? So our mean was 100%. I put that as 1.0, and our standard deviation of 0.15. So that gave me 0.9213. What is this value right here? Well, this is our z value from our normal distribution. What it means is that 92.1% is the lower bound of our Wechsler IQ score, right? So this would be the IQ score that we would say separates the lowest 30% from the highest 70%. On the flip side right here, right, if we went in for our 70% group, the score of 107.9% IQ score separates the bottom 70% from the top 30%, right? So the middle 40%, of our population taking this Wechsler IQ test will have a score between 92 and 108 approximately, if we were interested in figuring that out. All right. Well, there we go. Good luck on your assignments this week.